So I had already circulated the reference for this. So this will be a course on field theory at finite temperature. And the reference is a review article. But this will actually have more details than what I'll be able to cover in this, okay, because this doesn't assume too much about quantum field theory. Okay, it builds everything from the scratch, whereas I'll assume knowledge of quantum field theory at the level of the 2 graduate courses. So today I'll start with quantum mechanics at finite temperature. We'll basically try to reproduce some of the known results. But this, along the way, we'll also develop techniques that will be useful for quantum field theory. So here, the most, well, at least one of the most important things that one wants to calculate is the partition function. So trace e to the minus beta h, where beta is 1 over t, and h will take to be the simple one particle Hamiltonian in one dimension, e square by 2m plus b of t. And our goal will be to try to develop a path integral approach for calculating this partition function, because that's what we will be using in quantum field theory. But at the same time, in quantum mechanics, of course, you can directly evaluate this partition function. So you can check whatever we learn in using path integral against the direct calculation based on calculating the trace. So we develop a path integral approach. We develop path integral approach for calculating this. And we will see that this is very similar to what you do in normal zero temperature quantum field theory, but there are some important differences that you have to take into account. So let me start by writing down some normalizing convention. So we'll choose the usual basis of states. So the state Q will be the eigenstate of the operator Q hat. Okay, this is the position operator. Similarly, P hat on T. Our normalizing convention will be as follows. So Q prime will be delta Q minus Q prime, and the momentum eigenstates will have a 2 pi delta Q minus Q prime, sorry, delta P minus Q prime. And with this, we also have QP as e to the IQ. Okay, so these 2 pi is important, otherwise there will be some 1 over 2 pi factors over here. We also have the completeness relation. Which is integral dq is identity and integral dp over 2 pi based on this you can check the various consistency relations. Okay, for example, suppose you want to calculate q prime, but you do it by inserting a complete set of states between q and q prime, okay, using this completeness relation. And now you see that this is e to the I q p. This is the complex conjugate of q prime p, so e to the minus I q p prime. Sorry, I q prime p. And when you carry out a p integral, you indeed get delta q minus q. Okay, which agrees with this over here. But you can see also that without this 2 pi factor, you will not get the correct answer. Okay, so it's important to keep track of these 2 pi factors. Other questions? Okay, so now let's start calculating the partition function z, which is trace e to the minus beta h, and these are right as integral dq q e to the minus beta h u. Okay, I'll not always write the operators because it should be clear from the context whether we are talking about operators or classical objects. So we use the fact that you can calculate the trace in any basis, it doesn't matter what basis you use, and so I use a q basis for this. And then we proceed as you will do in normal path integral approach to quantum mechanics. Namely that we divide this into many small pieces, e to the minus epsilon h, e to the minus epsilon h hat. Okay, n of these, so n times epsilon is beta. And then start inserting complete set of states in between. So here I insert integral dpn by 2 pi dqn dn Okay, all I have done is to insert two factors of identity. Because integral dpn over 2 pi, pn is identity, integral dqn, qn is identity, so identity times identity. And similarly, we do it here. We put integral dp n minus 1 by 2 pi, dq n minus 1, dn minus 1, dn minus 1, qn minus 1, qn minus 1, and so on. Okay, it goes all the way here. So here I just insert q1, q1. Okay, I could have inserted q1, q1 also, but of course q1 with q will give a delta function. Yes, which q1 is just good enough. Okay, and you see that this is the correct counting. You start from n here, and then the n of these objects. Okay, so if this is n minus 1, the last one will be 1. questions? So now, let's try to rewrite this in a slightly more convenient form. Okay. Now, first you see that, here let me write this integral, e1 pi. There is a little asymmetry between the p's and the q's. For every p here, okay, there is a q. Okay, so here there is no problem. Okay, so pn is there, qn is there, integral. Okay. Last one has only p1 integral. Okay, no q1 integral. Okay. But that is compensated by the fact that there is an explicit q integral because of the trace. Okay. So I can declare this as our q1. Okay, so to make things symmetric. So declare that q1 by definition is q. Okay, of course it's just dummy index, so I can always change this q to q1. But I'll do something else. I'll also declare that qn plus 1 is equal to q. Okay, so qn plus 1 is not an independent variable, but I just introduce qn plus 1. Okay, as which is equal to q. Okay, which means this is also equal to q1. So now this integral takes the following form. Okay, there are n q integrals and n p integrals. Then you have the structure q I plus 1 e to the minus beta h hat pi, the product from I equal to 1 to n I equal to 1 to n, right? And okay, so let's say this is true. So first, this q is qn plus 1, right? So qn plus 1 e to the minus epsilon h hat, epsilon h hat, and here you are inserting pn, right? So for I equal to n, this term for I equal to n,
so there will be epsilon in place of beta.
sorry, epsilon. Thank you. So the first term, okay, is the I equal to n term over there, okay, the leftmost term. Then we have pn qn, okay, that's the I equal to n term again, pn qn. Next, you have the matrix element between qn yeah. So you are inserting qn e to the minus epsilon h hat pn, or pn minus 1. Okay, so that's the I equal to n minus 1 term. Okay, and then similarly pn minus 1, qn minus 1. Okay, so this is the general structure. Last term is p1 q1. This is p1 and q is q1. Okay, so this is the reason I have set q1 and qn plus 1 both equal to q. Right? Because only in that case that we can write it in this neat form. Because this I equal to n, qn plus 1 and q1 are both q in the original trace. Okay, that's the reason we have set this convention. Okay. So now our job is to try to evaluate this, and the goal will be that we want to try to integrate out the pi's, okay, because you want to write the path integral in terms of qi's only. Okay, the path integral involves configuration space integral. Okay. So the pi's are you want to integrate out. So this is easy. Okay, this is e to the minus I dy prime. These sides are the same as this side. This is square root of minus 1. Okay. Here, okay, this is a little, you have to do a little more work to evaluate this. So let's write it in the following way. You see, this is qi plus 1 e to the minus epsilon h hat. So h hat is the sum of two terms, p hat square. Let me write h hat is p hat squared by 2m plus v of q hat. So you have e to the minus epsilon times this. But I'll write it as e to the power minus epsilon times v of q hat e to the power minus epsilon e to the power minus epsilon p hat square by 2m I. And then, so what I'm doing here is that I'm using the Vcs formula to write exponential of sum of terms, okay, as the product of the corresponding exponential. So e to the a plus b, I can write as e to the a times something which involves e to the ab commutator times e to the b. Okay, so this is the e to the a part, this is the e to the b part. Here you have the e to the power that ab commutator, but whatever it is, it's e to the power epsilon square times something. Okay, that's important. Why it's epsilon square? Because it's epsilon times epsilon. A commutator will involve epsilon square. So this I can write. Okay, now we see that this is an eigenset of q hat. So e to the minus epsilon v of qi plus 1. This is e to the minus epsilon times pi square over 2m. And then we have qi plus 1 e to the power epsilon square times something pi. So this is like the inner product between qi plus 1 and pi. The leading term is 1, okay, plus of order epsilon square. But the order epsilon square terms, how many of these terms are there? N such terms. Okay, so you have like e to the epsilon square times something, okay, which you don't know. Okay, but you take the product of this n times. The product of this n times will have e to the power, will roughly go as e to the power n times epsilon square. Now you are taking the epsilon goes to 0 limit, getting n times epsilon fixed. Right? That's beta. Okay. So e to the epsilon square, okay, multiplied n times, okay, will always be of order 1, will just close to 1. In the epsilon goes to 0 limit if we keep n epsilon fixed. Is that clear? That's the standard argument for path integral, that when you make this finer and finer, the correction to this that you will get, you can ignore. Okay, so this term we just set equal to identity. Other questions? So let me write it. So basically you get z as integral product I equal to 1 to n dqi over 2 pi and then exponential minus epsilon sum over I of qi epsilon sum over I pi square by 2m, and then we have I. You already had e to the minus I qi pi, right? Here you have a qi plus 1 pi, so that's e to the power I times qi plus 1 pi. So e to the power I qi plus 1 minus qi times pi. Is this clear? Okay, so one factor came from here. Okay, that's straightforward. Other factor came after using the fact that this e to the epsilon square, I can just replace the identity, because the difference from identity, even if you take product of n such terms, is still close to identity. So then you just have qi plus 1 pi, okay, and that's e to the I qi plus 1 pi. So now we can do the pi integrals using standard Gaussian trick. Okay, we complete the square and do the pi integral. So I'll write this as integral. Okay, let's do the pi integral separately. The pi integral is integral dpi by 2 pi e to the power minus epsilon pi squared by 2m plus I pi qi plus 1 minus qi. So this I'll write as integral dpi by 2 pi for minus epsilon over 2m pi okay, I have completed the square. Okay, and then subtracted off the term which is extra. So this gives you 1 over 2 pi and then square root 2 pi m by epsilon the Gaussian integral e to the power minus 1 over 2 epsilon m y plus 1 minus y square. Okay. So let me write this factor a little better. So it's like square root of m n over 2 pi beta Okay, so this is the result of the pi integral. Now we can just substitute and express the partition function just as an integral over the qi variables. So we get z integral product I should have written m over 2 pi beta to the power m by 2. Okay, there n is part of that, and then integral
in the second summation, it runs from 1 to n plus 1.
1 to n plus 1 here?
Yeah.
No, I think it should still be 1 to n, right? Because there are n such terms. Okay. See, I equal n plus 1 is the same as 1. Okay. So v of q1 is not there. See, it starts from vqn plus 1, you're right, because you are starting from there, right? But it goes up to vqn plus 2, vq2, right? And now the vqn plus 1, I'm just replacing by vq1. Okay, that should be only n terms here. Is this okay? Okay, I'm just using the fact that this, I mean, how did we get this? I mean, because we had to begin with, we started with vqn plus 1, then vqn minus 1, it went up to vq2, right? There was a vq1 because the last one, the q1 came from the q on the right hand side. Okay? But I'm just using the fact that vqn plus 1 is the same as vq1, okay? Because qn plus 1 has been declared to be equal to q1. So this thing which comes in the inside the square bracket, I can write as a discretization of the Euclidean action. Okay, so this normally write as minus AC, which is minus integral d tau okay, if you take an expression like this and discretize it, dq dt will be replaced by qi plus 1 minus qi by epsilon. Right? That's the discretized version of velocity. Okay? When you square it, that's this term. When you convert the integral into a sum, you have to multiply by the interval, that's the epsilon, which is appearing here. And similarly for this. So this is what we call the Euclidean action. So let me write now formally. So formally this is written as n over 2 pi beta to the power n by 2 integral dq. Okay, this is the path integral over q exponential minus the Euclidean action. Where minus the Euclidean action by definition is this. So now we can try to understand the difference between this and the usual path integral that we do in quantum mechanics. In the usual path integral that we do in quantum mechanics, this integral typically runs from one value of tau to another value of tau, and you put a boundary condition that initially we had q equal to q1, finally had q equal to q2. Okay, that's the path integral. Here instead the integral is running over periodic configurations of q, right? Because the fact that qn plus 1 is equal to q1 translated in the continuum language by saying that q of beta is the same as q of 0. Right? It's like a cyclic configuration that when you have shifted the argument of when you shifted q by beta, right? So q1, so what is the difference between qn plus 1 and q1? So we are using the fact that tau is essentially I times epsilon, right? I is at the discrete points. So this is I equal to 1, 2, 3 up to n. Individual distances is epsilon, right? That's the way you are thinking of the discretization. So when you shift I by n, that corresponds to shifting tau by n times epsilon. But n times epsilon is beta. So by saying that q1 is equal to qn plus 1 is equivalent to saying that q is a periodic function with period beta. Okay, this is one crucial difference between what you do normally at zero temperature field theory and finite temperature field theory. That you take the variables to be periodic functions of Euclidean time with period beta. Is this okay? The second important difference is that normally in quantum mechanics or quantum field theory, you ignore this p-factor. You ignore this p-factor because typically you are only calculating ratios, right? You are interested in calculating correlation function, where you calculate ratios of path integrals of this form, and the p-factor goes away. But here we see that the p-factor actually depends on temperature, right? And a partition function, okay, is this integral. You are not taking ratio of that to anything. And what we want to compute is the temperature dependence of the partition function. Okay? So you cannot really ignore the p-factor. Okay? The p-factor has a temperature dependence. Okay? We will see that there are indirect ways of determining the p-factor, but you have to keep in mind that whatever you calculate with the path integral has a missing p-factor. Okay? If we just calculate this part, then it has a missing p-factor which can depend on the temperature, and that is something you have to take into account. Okay, this is a complication that was not there at zero temperature quantum field theory. Okay, and we will see how we handle this. Okay, this fact that there is a p-factor that depends on temperature. Okay, are there questions? Now let me just also write down a quick way to go from the Euclidean and the Lorentzian action.
Sir,
Yes.
here in the prefactor it depends on the n, right? How many number we divide.
Yes.
So,
That means that this will also have an n dependence,
right.
which will cancel this. Okay. But we will see that that's not the way we will determine the p-factor. We will use a indirect method to find out what the p-factor is. Okay. But at this stage, you have to just remember that there is a missing p-factor that you have to take into account. Okay. And particular feature that we will be using, right, to determine the p-factor is that this doesn't depend on the details of the potential. Okay. So we can, while calculating this directly is difficult because of the problem that you are saying, right? There is an n dependence. Okay. If you want to calculate, for example, the partition function for two defined choice of potentials, then the ratio doesn't depend on this. So ratios of two different partition functions, so different choice of potential, is easier to calculate because it's not sensitive to this factor. So what we will do is that we will calculate the ratio, and then independently we will calculate the partition function for one particular choice of potential, which is easy to calculate. Okay, and from that you can determine the original partition function.
So in that case, the beta dependence will also go away. So if we take the different potential, the temperature is something that we are doing.
It will not go away because the partition function has a temperature dependent function, is potential independent, but this also depends on temperature, right? So it will not go away, right? So this part will be the temperature dependence that comes from this part will determine, right? And then the temperature dependence that comes from some reference potential will determine independently, right? And that will tell us how to calculate the full partition function. Yes.
Maybe this is premature, but does this happen in expansion in beta? That is, can I think of it as corrections to a classical answer?
Yeah, so we'll do the high and low temperature expansion eventually, right? And in fact, in quantum mechanics itself, yeah. So we can expand it beta, okay? And we'll say there are some subtleties, right, which are not so severe in quantum mechanics, but which will come to haunt us in quantum field theories. Okay, so as I was saying, let me just say a few words about the relation to Minkowski action. Okay. So normally in the Minkowski or Lorentzian action, we write in this way, right? Integral dt, dq dt squared, m by 2 dq dt squared minus p of q. So to see how the Euclidean action comes, basically if you replace t by minus I tau, This becomes minus I integral d tau minus m by 2 dq d tau square minus v of q. Right? Because I just use t going to minus I tau, okay, and then dq dt whole square become minus dq dt whole square. So this is basically I times the equilibrium action. Okay. So if you remember in the conventional path integral, the weight, the factor that you use as weight is e to the is. This is the Minkowski action. So this under this weak rotation, okay, which is t goes to minus I tau, just becomes e to the power minus ac. Okay, and that's what we are seeing here. Okay, so it's the same e to the is. Okay, but because we have made this analytic continuation, okay, it has become e to the minus I ac. And this analytic continuation also is easy to understand. Why? Because normally in quantum mechanics we evolve by e to the minus I h t, and when you take t to minus I tau, it becomes e to the minus h hat tau. Okay, so instead of evolving in the usual time, okay, we evolve in the Euclidean time, which is related in the tau space, and because that's what you need to calculate trace of e to the minus beta h hat. Right? We are evolving in the Euclidean time by distance beta and then taking the trace. Okay, so what I am going to do now is to illustrate this for harmonic oscillator. Okay, that how we can use path integral to calculate partition function for a harmonic oscillator. Okay, but are there any questions before that? Well, I should have said this before, but let me do it now anyway. That I'll be using throughout h bar equal to 1. Okay, and I have been using h bar equal to 1 already.
So
Yes.
if I wanted real-time correlations at finite temperature,
Yes.
could I have generalized the scheme you had earlier?
Well, you can, but that's a little more complicated. We will see how it works. Basically, the one way to do this, we'll do first the Euclidean correlator, okay? And then one can show that there is the real-time correlator and the Euclidean correlator related by analytic continuation. That is in the configuration space. Okay? But if you want to do it in the momentum space, right, that's a little more tricky. Okay, and I think there are various methods by which you do that, but it's certainly easier to use, for example, this thermophile double formalism than this one. But in principle, the Euclidean Green's functions do have information about the real-time correlation function, because in the configuration space, you can show that one is the analytic continuation of the other. So we'll do the imaginary time correlation function based on this, and real time we'll discuss later. Okay, so here V of Q is half m omega square Q square. The energy levels are of course well known, n plus half omega, and the partition function, which is sum over n e to the minus beta en, okay, it's very easy to evaluate. It's e to the power minus beta omega by 2 over 1 minus e to the minus beta omega, which you can also write as 1 over 2 sin hyperbolic beta omega by 2. So if you are trying to, if your goal was to calculate the partition function of harmonic oscillator, of course you are not going to do path integral. But we will be doing path integral on harmonic oscillator, and we will show how the same result can be recovered. Certainly for harmonic oscillator it's not the most efficient method, okay, but we will see that that method can be generalized to quantum field theories, okay, which is where you may not always have the implicit spectrum. So let's start doing path integral. So here it's given by some function, let me call it C of t. Okay, this is the p factor, we don't know, that's all these factors which are sitting here. Okay, we just call it some function of type. And then integral dq e to the minus AC. The way we had arrived at it, the integration dq corresponds to breaking up the paths in lattices, okay, and then integrating over each qi. Okay, that's the way we have thought about this. But once you think of this as sum over paths, we can try to perform the same integral in different ways. And what we are going to do is to perform the same integral by thinking of this in momentum space, okay, or in the Fourier transform space. So Q is supposed to be a periodic function of tau of period beta. So any such periodic function can be decomposed into Fourier expansion. So I write Q of tau as sum over n, Q tilde n to the power I n tau 2 pi I n tau by beta. Okay, this is also often written as sum over n Q tilde n to the I omega n tau, omega n is 2 pi n by beta. And I think of integration over Q tilde over the paths as integration over Q tilde n. Okay? But there are some subtleties here. Okay, we have to check whether the Q tilde n's are real or complex. Okay. So Q of course is real. Okay, so using the requirement that Qt star equal to Q tau star is equal to Q tau, this tells us that Q tilde n star as Q tilde minus n. So we can take Q tilde n, if we take Q tilde n equal to an plus ibn, Q tilde n itself is not necessarily real. Then we have a minus n is equal to n, b minus n is equal to minus bn, and b0 is 0. For n equal to 0, a0 is the only variable. Is this clear? So when you say that we integrate over Q tilde n, what we mean is that we integrate over an and bn for n equal to 1 to infinity, because a minus n and b minus n are not independent variables. So you integrate over an and bn from n equal to 1 to infinity, and you integrate over a0, because b0 is 0. Okay, so these are our real variables. So what is you have to integrate? A and bn from n equal to 1 to infinity on and a0. Okay. We can in fact also think of this as independent integration over Q tilde n, ignoring the fact that these are complex. Okay, often we have seen that we can, if we have integration over complex variables, so we can treat as if they are integration over real variables. Okay, so you in fact, I mean, not make a mistake. If we had just thought of Q tilde n's as real variables and integrated over all Q tilde n's from minus n to infinity, okay, it will effectively give the same result. But here, let's be careful and do things explicitly.
You can work with sines and cosines.
We can work with sines and cosines. Yeah, you can work with sines and cosines. Basically, ans and bns are effectively that. Sines and cosines, exactly. So an multiplies cosine and bn multiplies sine, right? That's why b0 is not there, because sine of 0 of course is 0. Okay, so in this we can now calculate AC. So AC is half integral half m integral, right, integral 0 to beta half m dq d tau square plus T of q, sorry, right, half m omega square q square. And once you substitute, you can easily evaluate it. You can just substitute this and evaluate this. And I'll leave it as an exercise to check that this is the exercise. You get m. Oh, I should have done something else. Okay, this is just a matter of convention, but let me do it anyway. So normally when you do this expansion, you include a 1 over beta in this expansion. Okay, let me put that in. Okay, this is just a normalizing convention, it makes no difference at the end. So I'll need to put a 1 over beta in the expansion. Okay. So that's how you get a m over beta, because when you take the square, you get 1 over beta square, and then the integral gives you a factor of beta. Okay, so 1 over beta square times beta gives you a. Sum over n equal to 1 to infinity. Okay, this is what you get by substituting. Okay, just directly calculate dq d tau, okay, and integrate over tau. Integral dq will think of as integral some other function which can also depend on temperature. Comes integral product n equal to 1 to infinity en en and dA0.
Vt also contains this Jacobian factor.
Yes, so Jacobian is what I'm calling Vt, and the point is that this change of variable, right, of course depends on temperature, depends on beta. Okay, so this Jacobian can depend on beta, okay, but the Jacobian doesn't depend on any details of the potential, right? Which in this case means it doesn't depend on omega. And omega is the one which contains harmonic oscillator potential. So that's why I've written the V as a function of t, but no dependence on any parameter of the potential. So now we substitute here. This gives you C of t, B of t, integral product exponential of minus of this.
Second is also minus.
Minus, thank you. So this is a Gaussian integral, right? We can easily do this. C of t. Is this okay? Right? Here, because you have integration over n and pn, there is no square root. Right? Because each gave a square root, but you just square it. And here there is a square root. Okay, I am just using the fact that integral e to the minus alpha x squared dx from minus infinity to infinity is equal to pi by alpha. That's the Gaussian integration formula. Okay. But you can see that this is somewhat of a mess because it's an infinite product. You don't know what to really do with it, right? Because as you go to higher and higher n, for example, omega n is increasing, right? It's becoming larger and larger denominator. Okay, and if you take the product of infinite number of these, it seems to go to 0. Okay. So this is where all these fact there are various infinite factors that are on the way comes into play. Okay, and you have to try to handle this carefully, and that's what we'll try to do. Okay. And I should emphasize that whatever you are doing here, okay, we'll be doing throughout in quantum field theory. Okay, because after all, in quantum field theory, in perturbative quantum field theory at least, okay, the way you evaluate various correlation functions is by perturbation expansion, by applying Higgs theorem. Okay, and that basically means that we use the correlation functions in the free field theory. Right? The only correlation functions that we need to do a perturbation expansion are the products of correlation functions in free field theory, and then we integrate. Okay? And the free field theory correlation functions are just harmonic oscillator correlation functions. So once we know how to handle harmonic oscillator, we basically will also know how to handle quantum field theories. Okay? Although there are various additional subtleties that we'll see that comes in. Okay? So it's not a totally idle exercise, right? To do this. Okay, just to reproduce that simple formula that we got from the Hamiltonian formulation, right? 1 over 2 sine hyperbolic beta omega by 2. Okay, we'll eventually get there. Okay, but it will take a while. So this is okay so far? Okay? So now what we are going to do is to compare this with Z0. So what is Z0? Z0 by definition is the same partition function but at 0 potential. Omega goes to 0 limit. But that is a problem. Okay, that has problems, because you can see that as the omega goes to 0 limit, this blows up. Yeah, so you don't expect Z0 to exist. Okay, because this is showing that there's a diverging factor in the omega goes to 0 limit. Now you can also see where this divergence is coming from. It's coming from A0 integral, right? So what is A0? A0 was the constant part in the expansion of Q. So which means that if you take the average of Q over the whole interval, okay, that's A0. And that integral is going to infinity. Okay. This is not a surprise, because in the absence of a potential, there is nothing that restricts the average value of Q over the interval beta, right? The average value of Q can go anywhere, right? From minus infinity to infinity, okay, without any cost in the action, okay, because the potential term is not there, okay, in the omega goes to 0 limit. The kinetic term doesn't contribute to the 0 mode, right? If Q is constant, then the kinetic term doesn't contribute, okay, and that's the reason for this divergence. So what you have to do is that as you take omega goes to 0, you have to adjust the potential, so the potential actually corresponds to a finite box. Okay. So indeed you take omega goes to 0, okay, but at the same time make the potential infinite outside the range 0 to L. Okay, you assume that potential is 0 in the range 0 to L and it's infinite outside. Okay, that's like confining the particle in a box. Is this clear? Okay. And you take the box to be of large size. So if you do that, then as far as these integrals are concerned, it doesn't affect these integrals. These are non-zero modes. Okay, these are finite to begin with. Okay, so the fact that they are integrated, restricting the A0 integration range, this really doesn't make any difference. But the A0 integral, it makes a difference. Okay, because there is no exponential suppression in the A0 integral. Okay, so if A0 was allowed to run from minus infinity to infinity, it will give divergent result. But if A0 is now forced to run between 0 and L, then it gives a constant finite result. Okay, and that's what we are going to utilize. Okay. But let's first determine the range of A0. Okay, it's not strictly 0 to L, we'll see what it is. So let's look at the expansion for Q. So Q was sum over N, N Q tilde N e to the I omega n tau. So there is a 1 over beta, right? The expansion of Q, there is 1 over beta. So average Q is 1 over beta integral 0 to beta Q of tau. Yes.
We are in this box-like potential is that when we take omega, as we take omega to 0, this size increases.
No, so you are taking the omega goes to 0 limits. We are allowed to adjust V, right? So we are saying that now consider a new potential in which the potential is 0, except that it's infinite between outside 0 and L. Okay, that's our reference potential with which you are comparing the result. So you are comparing harmonic oscillator, okay, with another potential which is 0 from 0 to L, but which is non-zero outside the box of size L. Okay, in fact, the potential is infinite outside the box of size L. Okay, so it's confined inside that box. Is this clear? Okay, so average Q is this, right? Average over this interval beta. And in the normalization that you have used, you can see that this is the same as what? Q tilde 0, 1 over beta. Right? Because you get 1 over beta square, and then integral Q tilde 0, okay, integrated from 0 to beta, that's 1 over beta times Q tilde 0, right, which is 1 over beta times A0. Is this clear? So average Q is 1 over beta times A0. Okay, it's not exactly A0, then we have normalized. Average Q is 1 over beta times A0. Okay. So 1 over beta times A0 is forced to be confined in a interval of length L. Which means A0 is forced to be confined in an interval of length beta times L. Is that clear? With this normalization, okay, A0 range is beta times L. So A0 range is beta times L. So A0 range is beta L. And from that you can read out what Z0 is. So let's write it. I'll write it. Not sure I write it. Let's write it here. Okay, so any guess of what Z0 is? Okay, let's try to get from the formula. What should we do to get Z0? Okay, the potential now I have taken omega to 0, and the 0 mode we have restricted to a box of size L. Any suggestion is fine. You have to read out from that formula over there. Right? It's already there on the board. Z0 naturally should be the omega goes to 0 limit of that formula, right? That's not hard to figure out. What is the omega goes to 0 limit of that formula? These are okay, right? Omega goes to 0 limit of C of t times B of t. What is it? C of t times B of t, right? So let's write it. Okay, it's not very tricky what I'm asking. C of t times B of t. Okay? Now, omega goes to 0 limit of this one. What is it? Write the product with omega set equal to 0. Okay? Product n equal to 1 to infinity pi beta over m omega n square. Okay? And now the omega goes to 0 limit of this. What is that? The point is you cannot take omega goes to 0 limit of this, right? That's the reason why you have to do all this trick. So what should we replace this by?
Beta should be replaced by A0 by L.
No, not beta should be replaced by A0 by L. See, this whole factor,
Yes.
this whole factor was a result of doing the A0 integral with this weight factor, right? Yeah, so now this has gone, okay? But A0 integral range is beta times L, because 1 over beta times A0 is ranging over distance L, right? So I just replace this by beta times L. Okay, that is our Z0. Is this clear what you are doing?
Omega equals to 1.
Yeah, omega is 0, so this has gone away, right? Because this has gone away, you have to do this trick that if you really set omega equal to 0, right, Z0 is ill-defined because the 0 mode goes everywhere, right? So to handle that, we just put we didn't take the potential to 0 everywhere. Okay, we said it's 0 between 0 and L, okay, but it's infinite outside that range. Okay. And as long as L is sufficiently large, okay, that doesn't affect the integration over to non-zero modes. Okay. Because the non-zero modes are suppressed anyway by this factor, right? By the time you have gone to distance L, right, it's already highly suppressed, right? So the contribution from outside L is small anyway. Okay, so now let's calculate Z over Z0. So this is our Z. So Z over Z0, these cancel. Okay. Here we get product n equal to 1 to infinity omega n square over omega square plus omega n square. Then square root of 2 pi beta over m omega square, and then beta times 1 over beta times m. Is this okay? Okay. So now you see that if we can figure out what Z0 is, we are done. Okay, we just multiply by Z0 and get the answer. Okay. And at least the right hand side looks more manageable because this product we expect now is a finite product, right? Because as n goes to infinity, right, omega n's are becoming large, okay, but the ratio is going to 1. Okay. So the product of terms which approach 1, okay, has a chance to give a finite result. Okay. Whereas earlier the product of terms was such that when this was not there, right, the product of terms had this omega n growing at every stage, right? So you are getting factors which are smaller and smaller. So this now we expect will give a finite result, okay, and we will eventually evaluate this. But we have to figure out what Z0 is, right? And finally we have to also make sure that the L dependence goes away. Right? We will see that will go away once we evaluate Z0.
Written in this form,
Yes.
if we take once again Z omega going to 0, we
Yes.
should get left hand side is 1, right?
You should get left hand side equal to 1,
And right
except that omega goes to 0, right?
Yes.
You have to be,
Yeah.
I mean, a little careful because Z was defined without this length, right?
Mhm.
It was defined for non-zero omega, okay, but without this cutoff.
Yeah.
Z0 is defined for omega equal to 0, but with this cutoff, right? So in Z, if you take omega goes to 0 limit, you are going to get into problem, right? Because Z0 has been regulated, but Z has not been regulated, right? Okay, but we will see that Z0 will have automatically L dependence, which will cancel that. Okay, so when we now write the final expression for Z, okay, there will be no L dependence. Is this clear? Okay, now we calculate Z0. So Z0 is trace of e to the minus beta H0, right? This is a free particle Hamiltonian, okay, with Q restricted to a box. So this is integral dq Q e to the minus beta p hat squared by 2m Q. So I can write this integral dq Q p p to the minus beta p hat square q. But now because p is an eigenstate of this operator, I forgot the integral dp by 2 pi. We get integral dq integral dp by 2 pi e to the minus beta p square by 2m. And then we have QP. This is just one, right? E to the minus IQP times e to the IQP. So this, now Q integral, okay, we have to now use the fact that you have to put inside a box of length L. Okay, you can take it to a periodic if you like. So that gives you L. And then the P integral is a Gaussian integral, so that gives you 1 over 2 pi times square root of 2 m pi by beta. By m by beta. Okay. Now I should emphasize that this is a little, I mean this manipulation is strictly valid only for very, very large L, okay? Because if you really put the Q in a box of length L, then P is not continuous anymore, right? Then P is discrete. Okay, so you have to take that into account, but in the large L limit, doesn't matter, you can use this formula. Okay, you can check that by the fact that P is discrete, right, really makes no difference as you take L to infinity. So this is our Z naught. Okay. So now, multiply by this to get Z. Beta L 1 over beta L times 1 over 2 pi is equal to 2 pi by beta.
It's an L.
So this 1 is equal to 1 to infinity. Most of the terms cancel. So this 2 pi factors cancel, right? The square root of beta, this beta cancels. So basically you get 1 over omega times beta. Okay, so this is the path integral expression for the harmonic oscillator partition function.
But it's still ill-defined in omega 1 to 0.
Yeah, it is ill-defined at omega in the omega goes to 0 limit. That's not a problem because 1 over sine hyperbolic beta omega by 2. Remember that what you got by directly calculating the trace, right? That 1 over 2 sine hyperbolic beta omega by 2 was also ill-defined at omega goes to 0 limit. Right? So you expect the strict harmonic oscillator partition function to be ill-defined because as omega goes to 0 limit, the 0 mode becomes completely free. Right? So that's the infinity that you encounter. So now we have to show that this is what we had earlier. Okay, but at least now you are dealing with two finite quantities, right? Which has a chance of being equal. At least you can determine if they are equal or not equal. Again, I mean, I'm doing this because this kind of manipulation, exactly this kind of manipulation you have to do in quantum field theory many times, as you will see. So log z from here is minus log omega over t minus sum over n equal to 1 to infinity. Let me write it as log 1 plus omega square by omega n square. Okay, I just took the log of this and rewrote this as 1 over omega square over omega n square plus 1. So in this form, as n goes to infinity, okay, this ratio goes to 0. Okay, so it becomes log of 1, which is 0. Okay, so that what gives us hope that this is a convergent sum. Okay, and you can check that it is actually a convergent sum in the n goes to infinity. Okay, just by expanding the log, this falls off as 1 over n square. Okay, so sum over n, 1 over n square is convergent at n equal to infinity. So the way to evaluate this, well, there are many ways to evaluate this. Okay, one way to evaluate this is to not evaluate this directly, but evaluate its derivative. Okay, we calculate the derivative with respect to omega, and then we integrate it to get the result for as a function of omega. So what we have to calculate, we will calculate omega inverse del omega of log z. So this gives you, this is minus 1 over omega square minus sum over n equal to 1 to infinity. So when you take the derivative, you get 2 omega. I think this becomes 1 over omega square plus omega n square. Pardon?
In the first term,
There will be t.
no,
No, because this is omega over t, right? So it's like log omega minus log t.
Yeah, yeah.
So when you take the derivative of omega, t goes away.
Yeah.
Okay, so now the t dependence is only through this. So this I can write as sum over n from minus infinity to infinity 1 over omega square plus omega n square. Because these two, I had 1 to infinity, but I can also make it from 1 to infinity and minus infinity to minus 1. Okay, that took care of this factor of 2. And then the n equal to 0 term is exactly this one. Okay, so that's we have here. Now it looks somewhat manageable, right? Because omega n is 2 pi n by beta. So the way we do this, okay, let me write the expression and then we'll see how it works. So what is the idea that we want to write as a control integral with some integral which has poles exactly at y equal to 2 pi n by beta. Okay, that's not hard. You just write as 1 over e to the power I think I y beta minus 1, and then make sure that the residue is 1, you put I beta. So you say this function, okay, as a function of y, we have poles on the along the real axis, right? At integer values, at 2 pi n by beta. Okay, because whenever y equal to 2 pi n by beta, this vanishes. And the residue at the pole, okay, is 1 once you put this I beta factor. Okay, you can just expand and check that the residue is 1. So if we take the contour to be an anti-clockwise contour like this, Okay, this 1 over 2 pi I is included in the definition of the contour integral. Then that gives the correct result. Okay, that's the meaning of this contour integral. And now the idea is that we take this contour and deform it to infinity. At y equal to infinity, of course, this goes away, this vanishes. You can check that, in fact, this term itself vanishes at y equal to I infinity. And what you have is that you pick up poles from y equal to plus minus I omega. As you deform this contour, you will basically pick up the residues at y equal to plus minus I omega. That's these poles, right? So there are these poles over here, here and here. Those are the residues you pick up, but with opposite sign, because now you have a clockwise contour. And I'll leave it as an exercise to show that this gives you minus beta over 2 omega. These are the basically two residues that you pick up. Okay, and you have to do a little careful analysis to show that the integration from infinity doesn't give any contribution. Okay, the integral basically goes to 0 from infinity. Is this okay? So now you have, yes.
Sir, how are you defining the contour?
Pardon?
How are you defining it?
Oh, so the contour so this is the real axis. There are these poles on the real axis going all the way to infinity. The contour is like anti-clockwise contours are all these poles, right? So you can think of this as the difference between a contour like this and a contour like this. Okay? It has other poles at I omega and minus I omega in the y plane. So this is in the y plane. Okay? So you take the upper part of the contour, deform it to infinity. Right? In that process, it will pick up the residue from this I omega pole. Take the lower part, deform it to infinity. It will pick up residue from minus I omega. Right? So those are the two residues that I have listed here. And then you have to just show that the contribution from infinity vanishes. Right? So this part, that contribution from infinity vanishes, we couldn't have done directly in this. Okay? That's why you have to differentiate once. Okay? Because you need the fact that this falls off sufficiently fast at infinity. Is this clear? Okay, so that's the way you deform the contour and pick up the residue. Okay. And now we are more or less done, right? Because this omega inverse cancels this omega 1 over omega, right? So it's easy to integrate this. And by integrating this, you can show that log z is, there's an integration constant c, and then minus log 2 sine hyperbolic beta omega by 2. So it only remains to fix c. Okay. And now you fix c by taking the omega goes to 0 limit. Not omega equal to 0, but take omega goes to 0 limit. Okay. In the omega goes to 0 limit, this becomes c minus log. As omega goes to 0, this becomes beta omega by 2. That 2 cancels. Log beta omega. Now you look at the expression for log z directly. As omega goes to 0, this becomes log of 1. Right? So this term goes away. You get minus log of omega over t, so minus log of omega beta. So correct answer, required answer is minus log of omega over t, which is minus log of omega beta. This answer you get directly by examining the form of log z. These are no ambiguity, right? Because you are differentiating and integrating, there is an integration constant, but that you can fix by comparing with the original expression. So this means that C is 0. Okay. And that's the correct partition function. So as I said, we will be encountering integrals of this kind in quantum field theories. Here are sums of this kind in quantum field theory. Okay. And we will be freely making use of the fact that this expression over here is the same as this expression over here. Right? Once you have derived it from harmonic oscillator, right? This is a mathematical identity, so you can use it whenever you encounter a sum of that kind. Okay, so I think I'll stop here. So next time we'll be discussing correlation functions. Okay, this is a partition function. You can also ask for correlation functions, and we will see that the correlation functions can also be calculated both in path integral as well as in the canonical formalism. Okay, and give identical results. And then we'll move on to quantum field theories. Okay, and see how these apply to quantum.